Okay, class, we are going to look at this chapter, topic A, stoichiometry skills guide. And the one in your textbook looks like this. Okay, let me scroll up. Okay, yeah, the one in your notes looks like this, but we are not going to use this because I've condensed it in another booklet which I have given out to you. So it looks like this, the hard copy that I've given out to you. So we will revisit some of the mole calculations as a revision before we go on to look at the titration calculations. So please use this set of notes. This set of notes is actually compiled from the chapter that was in your term one book. But I reorder the questions such that, it flows better based on what I'm going to cover. Okay, first let's recap some of the formulas that give us the numbers of moles. So number of moles, as we know, we can obtain them by using mass over mR. So we usually take the mass divided by the total mR of the compound by summing up all the individual atomic mass from the periodic table. Number of moles is also equals to the number of particles over the Avogadro's constant, and Avogadro's constant is 6.02 times 10 to the power 23. So this Avogadro's constant can be found in the data booklet, section 2, I think. So you do not really need to memorize the value, but you need to be aware where to find the value. Okay. Now, for gases, if we have gases, number of moles can also be calculated by volume over molar volume. And there are two different molar volume that we are looking at. It depends on the conditions. So we have STP and we have SATP. STP stands for standard temperature pressure. And standard temperature pressure is referring to 0 degrees Celsius. And at STP, the molar volume is 22.7 dm3. So the molar volume of a gas at STP is 22.7 dm3. SATP is something new to you. It is like your RTP, room temperature pressure. It stands for standard ambient temperature pressure. So standard ambient temperature pressure is usually at about 298 Kelvin. And the value that we are using for the molar volume, in the past you used 24 dm3, but we are using 24.8 dm3 for IB. Okay, so SATP is referring to 298 Kelvin, 24.8 dm3 as the molar volume. So for gases, the volume divided by molar volume will give us the number of moles, because 1 mole of gas, 1 mole of any gas occupies a certain volume, which is the molar volume. So over here, we also have a new definition for relative atomic mass and relative molecular mass. In the past, we only look at the atomic mass compared to 1/12 of the mass of carbon-12, but now we have to include the weighted average of all the isotopes. So at atomic mass, relative atomic mass is the weighted average of all the isotopes' atomic mass compared to 1/12 of the carbon-12. So weighted average means that you consider the isotopes present and the rate proportion that they are found. Okay, so isotopes and their abundance. So example, if I have carbon, for example, if I have hydrogen, maybe I should use chlorine. If I have chlorine 35 and I have the chlorine 37, so that means when I get a sample of chlorine, I will have both of them. And they exist in different ratio. This exists as 75% of the amount as chlorine 35, 25% as chlorine 37. So when I get a bundle of chlorine, what I'm getting is I'm getting an average of containing 75% of chlorine 35 and 25% chlorine 37. So the weight will also be dependent on the isotope mass as well as the ratio that is present. So to factor that, we will call it the weighted average of the isotopes. Okay, weighted average of the atomic mass of the isotopes compared to 1/12 of carbon-12. So that's the definition of relative atomic mass. Okay, so we will also have one more formula that gives us the numbers of moles. Beside mass, beside particles, beside volume, we also have number of moles is equals to concentration times volume. So concentration multiplied by volume will give us the number of moles, and this is commonly used for titration. Okay, so let's look at some samples, and then we will just quickly go through the questions. So calculate the mass of an atom in Go 198. So in Go 198, we are taking into consideration that the molar mass is 198 grams per mole. And 1 mole of particles contains 6.02 times 10 to the power of 23 particles of atoms, right? So therefore, the mass of one atom will be 198 divided by 6.02 times 10 to the power 23 to find the mass of per atom, and that gives us about 3.29 times 10 to the power of minus 22 grams. Okay, so that's how we calculate the mass of atoms. So in this formula, we are using the idea of molar mass, which is the mass of 1 mole, and also the number of particles in 1 mole. Question 2. An accurate value of a molar mass is 18.01528 gram per mole. Calculate the mass of 1 molecule. So in this case, we need 1 molecule, and we need in kilograms. Okay, so 1 mole weighs this amount, and 1 mole consists of Avogadro's number of molecules. So for question 2, we will have to find out the mass of 1 molecule first, which is very similar, 18.01528 divided by 6.02 times 10 to the power of 23. And you will get the mass of 1 molecule as 2.9. Okay, so after you have gotten this, the answer is in grams. But the question says, give the answers in kilogram. So with this answer in gram, we will have to divide by 1,000 to convert it into kilogram. And if you do that, you will be getting 6.922 times 10 to the power of minus 26 kilograms per molecule of water. Okay, question 3. If the density of mercury is 13.534 grams per cm cube, and you have this amount of mercury, how many grams, how many moles, and how many atoms of mercury do you have? Okay, so let's clean up, and then we put in question 3. So question 3, density is equals to mass over volume, right? And we know that that's 13.534, and we know the volume as 62.5 cm cube. So take note, since this is cm cube and this is cm cube, we can multiply directly, and we get the mass. So that's how we answer the first part, how many grams. So the mass is equals to density times volume, and that is about 846 grams. Okay, next, they want to know how many moles is that equivalent to, and how many atoms do we have. So we will find the moles first using the formula moles equals to mass over mR. And mass, we have just calculated 846, and mR is given as 200.659. So calculating the number of moles, you'll get about 4.22 moles. So with 4.22 moles, they want to know how many particles. So remember just now we have a formula, number of moles is particles over Avogadro's constant. So moles will be 4.22. So we multiply by Avogadro's constant, then we'll get the number of particles, or number of atoms in this case. particles refers to atoms. So if we press the calculator, 4.22 times the Avogadro's constant, you'll get about 2.54 times 10 to the power 24 atoms. Okay, so we are just revising what you have learned previously in year 2 and year 3 and year 4 calculation, more calculation. Okay, we will continue with question 4, 5, 6, 7, going through the answer very quickly, okay? So how many hydrogen atoms are required to prepare this number of moles of propane? So in chemistry, mass is quite useless to us. So we don't usually deal with mass. So if we have questions in mass, we will always convert it into moles. So we are not given the MR, but you are given the atomic mass. Find the MR and then find the moles. So for this question, we will need to find the moles of C3H8, which is mass over MR. So mass will be 0.88 over MR will be 3 times 12.01 plus 8 times 1.01. So a question that you may have is that, can I use just 12 and 1? You cannot use just 12 and 1. You must use the value in the data booklet. Okay, so the value in the data booklet is 12.01. So with that, you will be able to get about 0.02 moles. Then the question is about hydrogen, and it's about hydrogen atoms. It's not how many moles of hydrogen atom, but how many hydrogen atoms. I repeat, it's not about how many moles, but it's how many hydrogen atoms. So before we can get to atoms, we need to find moles of hydrogen. So we can see that in every formula, you are seeing 8 moles of hydrogen. So therefore, if this is 0.02, this should be 8 times more than 0.02. So therefore, the number of moles of hydrogen atoms will be 8 times of 0.2. 8 times of 0.02, so will be 0.160. And that is moles. But question is not about moles. Question is about number of hydrogen atoms. So moles to convert into particles will be moles times Avogadro's constant equals to number of particles. So moles will be 0.160. Avogadro's will be 6.02 times 10 to the power 23. And then you work out the best answer for question 4. So it's about 9.6 times 10 to the power 22. Okay, question 5. All of the following statements are consistent with the concept of a mole except. Okay, so this type of question a bit troublesome. You got to look at them each one at a time. 1 mole of sodium contains this amount of atoms, which is correct because 1 mole of something always contains this number of particles. In this case, the particles is atoms, so this statement is correct. 1 mole of carbon-12 has a mass of 12 grams. So 1 mole will have a mass of the MR, which is 12 for carbon, if you check the periodic table. 1 mole of chlorine contains this number of molecules. So molecules referring to Cl2. Yes, 1 mole always contains this number of particles. But if it's asking how many chlorine atoms, then you need times 2. So this is correct. 1 mole of sodium chloride consists this number of ions. Now, why is it wrong? Because in sodium chloride, we get 1 sodium and 1 chloride. So the mole ratio is 1 sodium chloride to 2 ions. So therefore, the number of ions should be times 2. Okay, so this is wrong. D. Question 5. Calculate the mass of oxygen that can be obtained from decomposing this amount of water. So what we will do is that we take it that that's the amount that we have. Remember, number of moles. Okay, mass is not useful in chemistry, so we always do whenever we get mass, the first thing is to find moles. So we will find moles. 1802 moles is equals to mass over MR. So we take the MR as 18.02. So that will give you about 1, sorry, it's about 18.0. Yeah. So it's about 100 moles. So with 100 moles, then the next stage, after we find the moles of H2O, the next stage is always apply mole ratio. So first, always change mass into moles, then apply mole ratio. So the mole ratio will be 2H2O is to 1 oxygen. So therefore, the moles of oxygen is lesser. The moles of oxygen will be 50 moles. And then, but the question is not about moles, it's about mass. So to find mass, we will take the moles, multiply by the MR, which is 18.02. So we will have 50 times 18.02. But the question is asking in kg. So this mass is in grams. So the answer divided by 1,000 to convert to kg. So that will give you around 1.6 kg. Okay, last question. How many atoms are there in 18 grams of water? So water is H2O. So in the formula, we can see there is made up of 2H and 1O atoms. So 2H plus 1O. So therefore, 3 atoms per molecule. Per 1 H2O, it will be 3 atoms. So 18 grams divided by 18, right, which is 1 mole, but of H2O. But in terms of atoms, it will be 3 moles of atoms. And with 3 moles of atoms, we multiply by Avogadro's constant, and you will work out the number of atoms. So 3 moles times 6.02 times 10 to the power 23, you get 1.81 times 10 to the power 24 atoms. Okay, that is for the first part, recapping the formula of number of moles. Okay, after recapping on the number of moles formula, we are going to move next to the next calculation, which is the empirical formula section. So as I repeat, this set of notes is actually compiled from what you have in the term 1 book, but I just pick up the questions and sort them according to the skills. So this part, we're looking at the skills of doing molecular and empirical formula calculate determination. Okay, so after the earlier revision, which is the foundation of the chapter, we will move on and look at this part. So empirical formula is the simplest ratio of the atoms. So example, if I have, let's say, C2H4, that's not the simplest formula. The simplest formula will be CH2. So we will say that the empirical formula is CH2, while the molecular formula is C2H4. Okay, so molecular formula tells us the actual number of atoms present. So if it's C2H4, that means 4 hydrogen, 2 oxygen in one molecule. So the usual procedure for empirical formula, if you remember, it will be your table, whereby you are looking at in terms of the atoms. So sometimes you may have CHO, something like that, and then you will write down the mass. Sometimes you're not given the mass, then you write down the percentage. Okay, because if we take it as 100 grams, then percentage is mass. So you put in the mass, and then we usually find the number of moles from the mass. Okay, and then we always do, since it's a relative ratio, so we will divide by the smallest number of moles. And sometimes when we divide by smallest number of moles, we may just round to the nearest number. But it also depends, right? If I get 1.9, I may round it up to 2. Okay, if I get 2.08, I may round it up to 2. But there are some cases whereby you get 1.5. Then you cannot be rounding up from 1.5 to 2, or you get 1.49, something like that, 489. You cannot be rounding up it to down to 1, and you also cannot round up to 2. For this type of cases, we will apply point number 5. We multiply by a suitable integer such that we get a whole number. Okay, so if it's like 1.5, we will multiply by 2. But let's say you get 1.333, which is 1 1/3. Then you may want to multiply by an integer of 3 to get a whole number. Okay, so usually we divide by the smallest number of moles, we get the answer. But in the event that the answers are some like fractions number, like 1 1/3, or 1 1/2, 1 1/4, then we will usually have to multiply by an appropriate integer to get the whole number, because we can't do a round up from 1.1 1 1/3 to become 1. The difference is just too big. Okay, but if it's like if it is like 1.99, yes, we can put it as 2. Okay, so after we get the molecular formula, what's the relationship between the molecular formula and the empirical formula? The relationship between the molecular formula and empirical formula is that the molecular formula is n number of sets of empirical formula. Molecular formula is n number of sets of empirical formula. Okay, so example, if I have CH2 case, again, just now our CH2 case, so molecular formula is 2 sets of CH2. So that's why it's C2H4. So therefore, N will be 2 times C2H4. Okay, let's look at the examples, which is already worked out for you. So to recap the method, so first, the questions give us the mass. We will put down the mass. Remember, it's oxygen, not O2, okay? It's O, because we're looking at atoms, not O2, not molecules. So do not put 32 over here. This is not 32, it's atoms, okay? Then we'll take down the mass. We write down the MR if you want to, or write down the AR from the periodic table and you find moles. So after you got the moles, you divide by the smallest number. So the smallest number is about 0.399. So if you divide throughout and you get something like this. So remember, if it's like very close, we can do a round off. But if it's 1 1/2, we cannot round half up to become 2. So we understand that this is 1 1/2. So we will multiply by the factor of 2 to remove the denominator. So we 2, 2, 3. So we know the formula is Na2S2O3. Okay, that's how we get the empirical formula. And the molecular formula is how many sets of this basic formula. Okay, so let's look at an example here on finding molecular formula. So given empirical formula is CH2O and MR is 180, which is the molecular mass. So what is the molecular formula? So how many sets of CH2O will give me 18? How many sets of CH2O will give me 18? Right? So I have to find the mass of one set of CH2O, which is 30. And how many sets of it will give me 18? Roughly 6 sets. So therefore, we know the actual formula has to multiply by 6. So 6 times of CH2O will give me C6H12O6. So that's how you work out from an empirical formula to molecular formula. So the key is we need to know the MR. If we do not know the MR, then we cannot find the molecular formula from an empirical formula, because we need the MR to help us to calculate. Okay, so question 3 over here is a practice for you to try out what we have just covered. Okay, so let's look at question 3. Okay, I give you some time to do. You may want to pause the video if you want to try. So if we draw the table, okay, so you have a CHO 62.1, 10.3, 27.6. So we find by the number of moles. So it'll be 62.1 divided by 12.01. And then this will be around 10.3 divided by 1.01. Oxygen, I think, is 27.6 divided by 16. Okay, so you divide to find the number of moles. And at the end, you'll find that roughly, the number of moles is about 5.18. It's about 10.3. It's about 1.73. So we need to divide by smallest number, which is 1.73. So we divide by 1.73, and that will be approximately 3. So if you take a calculator, 5.18 divide by 1.73, you get about 2.994, which we will just approximate to 3. Right? So therefore, we will not write the 2.994, but we put it as 3. Okay, so the same for the rest. You get about 6 and 1. So the empirical formula is C3H6O. Okay, the molecular formula is a bit difficult, so let's look at the molecular formula. The question says when 0.125 gram of it evaporated in a syringe at STP, this is the amount of vapor. So remember, if I have an empirical formula and I want to get molecular formula, I need MR. So I need to find MR, right? So I have a volume, and I understand that number of moles is equals to volume over molar volume. So I can try that first, 24.1. This is cm cube, not dm cube. So you have to convert it to dm cube, or you convert your molar volume to dm cube. So at STP is 22.7 dm cube. So 22,700. 22.7 dm cube is equals to 22,700 cm cube. Okay, so because it's cm cube, so this has to be cm cube. So with that, you will find the number of moles, which is around 1.061 times 10 to the power minus 3 moles. But that's not MR, right? So what else do we learn? We learned that moles equal mass over MR. So moles will be 1.061 times 10 to the power of minus 3 moles. And if we need MR, then the formula will be MR is equals to moles over, MR is mass over moles, right? So mass is 0.125. So we put in 0.125 as the mass. And moles was 1.061 times 10 to the power 3 minus 3. So put the moles down. And then with that, we will be able to find MR. It's about 117.8, around that. If it's slightly different, it's fine, okay, like because of the rounding off. So 117.8, and that's the MR. But it's not the question. The question is molecular formula. The question is not find the MR, right? So with the MR, then we can find molecular formula. So what is the mass of one set of C3H6O? The mass or the empirical formula MR is about 58. Let me calculate. So carbon is 12.01, 3 of them, plus hydrogen is 1.01 times 6 of them, and then oxygen is 16, so it's about 58.09. So therefore, how many sets of 58.09 equals to this? So we can tell it's about 2 sets, right? So therefore, 2 times 2 sets of C3H6O, 2 sets of them. So the molecular formula is C6H12O. Okay? So that is how we do the empirical formula and molecular formula that we have revised before. We are just doing revision of what we learned. Now, this combustion data here is a bit new to you, so I would prefer to cover that in class. So what I'm going to do is we only do some revision of things that we learned before. Okay? So we will move on to bypass the combustion data, and we will look at this part on page 4. Scale 4. Scale 4 is about our dilution, our number of moles, our mole calculation of concentration. So remember, when we dilute something, the numbers of moles do not change. So let's say this was the number of moles of chemical, let's say number of moles of acid. So the number of moles of acid is so much. Right, you added in more water. So the number of moles or the number of circles in my diagram did not change. So number of moles do not change. So for dilution, we do not use mass over MR or volume over molar volume or particles over Avogadro's constant. We use concentration times volume. So concentration times volume is number of moles. So C1V1 should equals to C2V2, where 1 is before and 1 is after dilution. Okay, so understand this? Now, the units for concentration is usually mole per dm cube. Sometimes they call it molarity. Okay, but usually we use mole per dm cube, but molarity means mole per dm cube. If you want to express the concentration in terms of grams, that is also possible. It's called grams per dm cube. It's fine to express in this way. From mole per dm cube to grams per dm cube, how do we convert? Okay, how do we get moles per dm cube into grams per dm cube? So to convert a moles into grams, we multiply by mR. So the same for that, for moles per dm cube to grams per dm cube, we'll multiply by mR. Okay, another common units that we use for concentration will be something called ppm, parts per million. Parts per million means that if I have 1 million parts, 1 million of that thing, only one part is the chemical. So it's very diluted, you can tell. Like if for 1 million part of water, 1 million part of water, only one part is the chemical. So it's very, very diluted. And how is it related to the previous concentration we learned? 1 part per million is also known as 1 milligram per dm cube. Right? So remember just now, from mole per dm cube, we want to find grams per dm cube. We multiply by mR. Then from grams per dm cube, if we want milligrams per dm cube, then 1 gram is 1,000 milligrams. So we multiply by 1,000. So that's how we convert something into ppm. Okay, and so therefore, if I give you ppm, you should be able to convert back. So if I'm given ppm, then you convert by dividing by 1,000. Right, the opposite. That over here, instead of multiply by mR, you divide by mR. Everything is the reverse. Okay. Now, what we are doing, so in the many of our calculations, is that we also apply mole ratio. So mole ratios give us a comparison and allow us to find something. Okay. So sometimes when the equations, a few equations are involved, we may want to combine all the mole ratios together rather than to apply one and calculate and then use the value and calculate again to the next one. Okay, I'll give you an example later to show the combining of mole ratio. So most of the time when we solve a mole question, the first step we will do is write an equation. You don't have an equation, you cannot do a mole question. So you write an equation. And mass is useless to us. So we will convert all the mass usually to moles. That's the minimum you can do, is to convert the mass into moles. After you have the mass into moles, or you use your other methods to find moles that we have covered earlier, either volume, or you call concentration times volume, or molar volume, or particles. As long as you get moles already, the next step is to use mole ratio. Get mole ratio to find the moles. Okay, so it depends on the question. If the question say, find the mass, then you use your moles to continue to find the mass after you found the moles. If they say 5% U, then you use the moles to find percentage U also can, or you use your mass to find percentage U. Okay, so the idea is write equation, convert all the values to get moles, and then apply your mole ratio. Okay, so let's look at some examples that apply what we have just covered. So if I have a dilution, so if this is amount of diluted to a new volume, we don't know what is the new volume. So if we let the volume be V2, so we need, this is the volume to give me this concentration. Can you see it's a different concentration? So if you call it C1V1, then this must be the C2. So we apply the formula C1V1 equals C2V2 and we put it in to find the volume. Now this volume is not the volume of water to be added. So you read carefully. So if the question say what is the final volume, then yes, this is the answer. But sometimes the question say what is the volume of water to be added, such that I can do that. So the volume of water added is the final volume minus your initial 25. Then you get the volume of water to be added. So you read the question carefully, see whether they are asking for the final diluted volume or they are asking for the volume of water to be added. So if they are asking for how much water should you add in order to make that solution, then it will be, you have to add this amount. So read carefully. If the question say amount of water to be added, then this will be the difference. If you say what's the final total volume of the diluted solution, what is the final total volume, like this question, then it will be the C2. It's the V2, sorry. Okay, so this is an example of using mole ratio with concentration. So again, I have volume, I have concentration. So usually volume and concentration. First step, equation. Remember, first step was equation. Second step, find moles. So second step, we find moles. Third step, we apply mole ratio. Okay, so since they say magnesium is excess, so we use our limiting reagent to find the hydrogen. So the mole ratio will be 2 hydrogen, 2 acid to 1 hydrogen. 2 is to 1. So the moles of hydrogen will be 0.05. Okay, that's how we do it, right? Okay. Now, remember, I told you about combining mole ratio. If there are many moles, many equations, can I combine the mole ratio? Let me show you how to combine the mole ratio in this question. Okay, question 3. Calculate the mass of acid that can be produced from 5.6 gram of nitrogen. 5.6 gram. And I need to find this one. Right? So, of course, you can say, oh, I do 5.6 gram first, then I find ammonia, how much? Then I take the ammonia, and then I find how much NO. Then from the NO, I calculate and find how much NO2. Then for NO2, I find HNO3, which is possible, but very slow. So what we will do is that we will combine them together, and I want to find the mole ratio of N2 is to HNO3 directly. I want to find the mole ratio of N2. How is it related to HNO3 directly? Okay, by combining all the equations. So how? Let's look at the common items. So if we call this equation 1, 2, 3, 4, the common thing that links 1 and 2 is ammonia. The common thing that links 2 and 3 is NO. And what is linking 3 and 4 is NO2. And then finally to what we want. Right? And we started with N2. So we can see that all these items that I've highlighted are related. So for 1 mole of N2, I will get 2 ammonia. That's what equation 1 is telling me. And apply the 2 ammonia into equation 2 now. If I have 2 ammonia, what is the NO I'll be getting? Because I only have 2 ammonia, I get 4. So if I have 2 ammonia, then I should get 2 NO. Because 4 to 4, so 2 to 2. So if I have 2 NO, how many NO2 will I get? So 2 NO, 2 NO2, so it will be 2. Now, if I have 2 NO2, apply to the last one. If I have 2 NO2, how much acid will I have? I have 2 NO2, this is 4. So 4 to 4, so 2 to 2. Right? So remember at the start, I wanted the shortcut. I want to straight away link this to this and make it easier, bypass all the steps. So can you see a mole ratio of N2 to HNO3? So you can see N2, you can see HNO3. So the mole ratio is 1N2 is to 2HNO3. So instead of calculating all the intermediate steps, we are all going to bypass all of them. We're going to bypass all of them and straight away link this to that. Okay, so with that, let's try to solve question 3. Okay, I give you some time to try, and when you are ready, then you unpause the video. You can pause the video to try, and then when you are ready, unpause to go through the answer. Okay. Okay, so we need to find this is the mole ratio that we are going to work with, N2 to 2HNO3. So we find the number of moles of N2. Remember, mass is useless to us. Mass is useless to us. So we find the moles of N2. So you look at periodic table, what is the nitrogen again? Mr. So you get your mass 0.2 moles. So the 0.2 moles is moles of N2. So in mole ratio to HNO3, that will be number of moles of HNO3 will be 0.4, double. But the question is asking for mass, so we end off the mass with 0.4 times the MR. So the MR will be HNO3, so you add up the MR from your periodic table. Okay, the individual AR. Okay, roughly we should be quite close to 25.2 grams, something like that. Okay, we multiply by the MR. Okay, so this is an example of how we can combine multiple mole ratio so that we can bypass the intermediate step and skip the working, such that we take from the start and we quickly relate to the end. Okay, question 1. Let's finish with question 1 and 2. Question 1 is purchase standard solution of KOH has a concentration how much? How would you prepare this? To prepare 100 cm³ of the diluted one. So if this is C1, we need V1. Okay, and this is V2 and this C2. Right? So we can see that remember, cm cube meter cube, cm cube dm cube, so I have to divide by 1,000. So that's the volume in dm cube times 0.1. So this is C2 V2 is equals to C1 V1. Then you can rearrange the equation and you find V1. So if you let V1 be in cm cube, if you let it be, then you will get the answer in cm cube. In this case, I'm letting my V1 be in dm cube. So I will get a value of 0.1 times 0.1 divided by 1. So I'll get V1 is 0.01 dm cube. But let's say if you want it cm cube, you multiply by 1,000. So it's about 10 cm cube. Okay, remember to do this conversion is multiply by 1,000. Question 2, calculate the molarity of this. So remember, concentration can be in various forms and cube. So if you pay attention just now, milligram per dm cube is parts per million. It's also known as parts per million. Okay, they want the molarity. So what do you mean by molarity? That means they want the concentration in moles. They don't want it in milligrams per dm cube, but they want it in moles per dm cube. So what we will usually do is we will have our milligrams per dm cube, convert back into grams per dm cube first. And then grams is related to moles. So from grams convert to mole per dm cube. So this is 6.2. So change into grams, divide by 1,000. Milligrams to grams is divided by 1,000. So I divide by 1,000. So I'll get 0.0062 grams per dm cube. and then change to moles per dm cube, we multiply by mr. So the mr is oxygen, so it'll be 32. Right, so times 32. So I'll get about 0.1984 moles per dm cube. Okay, but let's say if you want to follow SF, and then you see this was 2SF, so following the least SF, you'll be 0.20 mole per dm cube. Okay, so we are done with this section. So we will go and revise scale 5, which is limiting reagent and percentage yield. And then we will maybe take a stop here, the scale 5. So scale 5, limiting reagent and percentage yield. Let me see what is scale 6. Scale 6 is direct titration. Okay, direct titration also can go through the examples. Okay, so we will start after direct titration. Okay, so limiting reagent and percentage yield. Limiting reagent, that is the one that is completely used up with nothing left in excess. Okay, and it's the limiting reagent that determines the theoretical amount of product maximum that you can get. It's a theoretical yield is determined by limiting reagent. It's the maximum that you can get. Okay, excess reagent is the one that is left behind after the limiting reagent is used up. Okay. So how do we identify limiting reagent? First, we must know how many moles of each reactant is present. And then we can divide the moles by the coefficient from the balance equation. Or we can just say, oh, if this number of moles is used up, how much of the other do I need? And then you check whether do you have enough to meet that need. If you have enough to meet that need, that means most probably that is in excess. If you have more than enough to meet the need, then that means it's in excess. If you do not have enough to meet the need, that is a limiting reagent. Okay? So that's how we determine limiting reagent. Yield, how do we know our yield? How much is our yield? Our yield will be the experiment, what you get over what theoretically you should be getting. So theoretically, what you should be getting is from the limiting reagent. If you remember, this was the theoretical yield is actually calculated based on limiting reagent in mole ratio. So theoretical yield is calculated by the mole ratio to the limiting reagent. Okay, so after you get the theoretical yield, you have done an experiment, you compare it against it, and you multiply by 100%. So that's percentage yield. Okay, so let's look at an example. So if this amount of calcium needs this amount of acid to react, so this is an example of limiting reagent. Okay, one question I always ask people is, when do you know that the question needs you to determine limiting reagent? I repeat, when do you know that the question requires you to determine limiting reagent? So many people do not know when. They just determine when the question asks, or the question say this one is must do the limiting reagent, then we will do it. But it's not true. So you will have to determine the limiting reagent whenever all the reactants amounts are given to you. I repeat, you will have to determine limiting reagent whenever all your reagents amounts are given to you. And how do they give you all the amount or all the reactants amount are given? How do they give you the amount? They may give you in terms of mass. They may give you in terms of volume for gases. They may give you in terms of concentration times volume. They may also give you in terms of particles. So as long as in some way they give you the amount of all the reactants present, you must determine limiting reagent. So you see this case, this one they tell me is 10 grams. This one they tell me is 200 cm cube of 1 mole per dm cube. So they gave me all the amount because in whichever way, all the values that they give me allows me to find the number of moles of each one. So I know all the amounts. So that means this question must do limiting reagent. Okay, so take the 10 grams, divide by the AR, so you get the number of moles of calcium. Then you take concentration times volume, you find the number of moles of acid. So then you ask yourself, for 0.2 moles of acid to be used up, since the mole ratio is calcium to 2 acid, right? So for 0.2 moles of acid to be used up, how much calcium I need? I need 0.1, right? Mole ratio 1 is to 2. So I know I need 0.1 calcium, and then I check, do I have 0.1? Yeah, I have more than 0.1, more than, right? So therefore, this is excess. So this is limiting reagent. Okay, so the limiting reagent is HCl. So you can see here. Now, next, we look at one example of percentage U. So remember, percentage U is over theoretical U, and theoretical U comes from the limiting reagent. So in a way, we have to determine limiting reagent. And also, if you read carefully, the question gives you 25 grams of this, and you have 28.5 grams. So this 28.5 grams is the experiment. Okay? And if this question, let's say, I know it should be stated, but it's missing. If it say excess oxygen, okay, oxidation of this in excess oxygen, can you add it in? Because I think this should be in the question. In excess oxygen. So if it's in excess oxygen, we take that that's the limiting reagent already, right? So 25 divided by the mass. So remember, my mass is not correct. You must use the data booklet mass. So data booklet mass will be 8 times 12.01, then plus 10 times 1.01. You must use the value in the data booklet, which is the weighted average of all the isotopes compared to 1/12 of carbon-12. Okay, but so therefore, you factor in the isotope, that's why there's a 0.01. Okay, so my example is not showing that, but you, during exam or during your practice, you must use the data booklet one. So 25 grams divided by MR, you get the moles. So that's a limiting reagent. So looking at C8H10 as the limiting reagent, I need to find the terephthalic acid, which is CH6O4, right? So it's mole ratio 1:1. 1:1. So therefore 0.236 is to 0.236, right? And with that 0.236, I multiply by the MR of what? Of C8H6O4 MR. So this is assumed this is the MR, but by right, it should have a 2 decimal place, okay? Because you should use like values like 12.01, 1.01. So you multiply. This is a theoretical mass. But why? Because it's based on limiting reagent and based on mole ratio. So you did your calculation based on all this is theoretical one. Because you do just, so the mole ratio is of the equation, and the equation is a theoretical thing, right? So we need, supposed to get 39.2. So the formula is experimental over theoretical times 100%, right? So experimental was 28.5. It was stated in the question here, okay? And theoretical is what we have calculated using the limiting reagent, 39.2. So 28.5 divided by 39.2. So 28.5 divided by 39.2. So that's the percentage yield that you're getting. Okay, so I think I have already done this part of the question, 28.5, right? So if you look at the example, we have already done this. This was the exact example. Okay, they say that if 25 gram limiting reagent, so which is what we have done just now, 25 gram, and we let it be the limiting reagent, right? So we have gone through this example already. So we just find the other example, calculate how much H2 will you get when this amount reacts with this amount. So the calcium is 0.623 and the HCl is 27.3 and 1.25, right? Mole per day cube. So we will have to determine the number of moles of calcium and number of moles of HCl. So because both numbers of the amount are given, since both amount are given, we will have to determine limiting reagent. So 0.623 divided by 40.1 is about 0.0155 moles. HCl will be 1.25 times 27.3 over 1,000 to change to cm cube, dm cube. So it's about 0.0341 more. So we can see from that is 1 calcium is to 2 HCl. So if this is 0.0155, this should be 0.0155 times 2. So take a calculator, 0.0155 times 2, so you get 0.031. This is what you need, right? If you want all to be reacted. So you check, do you have what you need? Sorry, it's with the HCl. You have what you need. Yeah, I have what I needed. I have what I needed, and in fact, this is in excess. So therefore, this is limiting reagent. So using the limiting reagent amount 0.0155, we will do the mole ratio with limiting reagent. Calcium is to H2 is 1:1. So number of moles of H2 will also be 0.0155 moles. Okay, and the question is asking for volume at SATP. So SATP, molar volume is, molar volume, we just recap on the first page, 24.8 dm³. So this moles number of volume will be equals to moles times molar volume. So 0.0155 times the molar volume, 24.8. 0.0155 times 24.8. So it's about 0.3844 dm³. Now the problem is how many SF do we keep to write? What's the number of decimal place? So 0.3844 dm³ can or not? So we read the question. Usually, remember what we are doing is we are doing multiplication and division. So we will follow the least SF. Right? So this is 3SF. So we will follow the least SF, 3SF. So I cannot leave my answer like this by right. So I have to change to 3SF, 0.384 dm³. Okay, this final answer should be 3SF because the least SF in the data is 3. Not because always must be 3SF, but you have to look at the data that you have used in the calculation. What is the least SF of the data? Then you will follow. Okay. Okay, so last part, direct titration. This all recapping. Okay, so direct titration. In the titration, we will have a titrant. Titrant is in the burette. And then we have our sample. Sometimes we call it analyte, which is in our conical flask. This is the analyte. And then the titrant is in the burette. Okay, and we have an indicator. An indicator give us the endpoint of the titration. So indicator give us endpoint. And equivalence point is when, based on the stoichiometric ratio, the amount added is equal to neutralize it. Equivalence point is the stoichiometric amount has been added based on the equation to neutralize something. Okay, or to react something. So usually titration calculation or any calculation start off with an equation. Start off with equation. Then find number of moles, either using mass or using concentration times volume, or using volume over molar volume, or using particles over Avogadro's constant. Okay, so find the moles and then apply your mole ratio. So let's look at this example. If this amount of acid was neutralized by this amount of NaOH, the solution was made from this amount of acid in 250 gram cm cube. Things but we do not know how to start, but at least we know we cannot take the 0.8 and try to divide by MR because we don't even know what is X. There's no MR for X. So, but at least we see one set of complete data here. And this set of complete data is concentration times volume, right? So first equation, write an equation. Second, find moles. So I'm going to find moles of using the concentration volume and get find moles. Then after you find moles, that's the second step. Third step, always mole ratio. So the mole ratio is with respect to H3X. So 3 sodium hydroxide to 1 H3X. So sodium hydroxide is this amount. So what is H3X? It will be divided by 3. So that's H3X. Okay. Question says that this is the number of moles of H3X. And this is in 25 cm cube. But you have 250 cm cube. So you read carefully here. You only took 25 to titrate, but actually you have 250. So that number of moles that you calculate was for 25. Okay, it's for 25 cm cube. So in terms of 250 cm cube, then the number of moles will be 10 times. The question is asking for finding the MR. So of course, if you do finding the MR, there are many ways to do it. One way is concentration by using moles over 25 ml. Then take the concentration times the volume, which is 250 to 5 moles. And then you take mass over moles to find MR. Of course, also I can do it at this stage. Another way, I use a proportion. Since 25 ml is 0.00286 mole. So 250 ml will be 10 times. So 0.0286 mole. Right? And this is the moles, and this moles equal to the 2.8 grams. This moles equals to 2.8 grams, right? So this equates to 2.8 grams. So MR is equals to mass over mole. So 2.8 over 0.0286. So you will also get the MR in this manner. Okay? Okay, so I think we will not go through the questions here, but we maybe stop around here. At least we have gone through the method. So, well, school starts, we will go through these practice questions since we already learned how to calculate. Okay, we'll look at the practice question, atom economy, back titration, and also the combustion, which I skipped earlier because the combustion is new to you. So I skipped the combustion empirical formula. Okay, so what we will do is that when school starts, we will go straight to recap on this part. We will go straight to this practice and then go through them. Okay, if you want, you can prepare first the practice questions so that when we go through in class, you can follow better, faster, and you can check your answers quickly. So we will be going through the practice question when school starts and then continue with skill number 7. And then skill number 8, back titration. So once we finish all the titration, then we'll go back to the combustion. Okay, so that will be your holiday homework. Holiday homework, watch this video. And if you want to, please also try practice the question because you know all this while I'm the one doing the questions. So it will be good for you to try. Then when you come to class, we will just go through. You just mark and then you just correct your mistakes faster. Okay, we stop here. Thank you.